Um, yeah, thank you to the organizers for inviting me. Rob emailed me a few days ago to replace another speaker who is currently busy taking care of patients. Since I'm not busy taking care of patients, I thought I'd step in. And I was left with a bit of a challenge of coming up with a talk in a few days. And I didn't want to rehash things that many of you have probably heard from me before. I wanted to try something new. And in keeping with Sandy's spirit of Math Onco as an inclusive community where we take ideas from wherever we can, I thought I would highlight some of the things I learned from working with 4 of my colleagues over the last couple of years, and lessons that I think will hopefully help all of us to work better on adaptive therapy and cancer treatment in general. So Katerina has this nice perspective on cancer treatment as a game between the tumor versus the doctor. And I think this is a very useful way to think about, what we're doing when we're trying to optimize our therapies. But there's a few important questions that come up right off the bat when we think about this model. And the 2 things that matter a lot to me is sort of the relative power of the 2 players, of the tumor versus the doctor, and also the rules of the game that they're playing. So that's kind of the 2 themes that I want to focus on. Most of the stuff I'll talk about is rather preliminary. Most of it isn't out anywhere. There'll be some published stuff in the middle briefly, but if you want more information, just chase down the people that I mentioned, and I'll be happy to tell you more. So I met Ryan about a year ago at a SFI workshop on biological computation. And Ryan isn't particularly interested in cancer, but he is very interested in understanding how evolution works. And in particular, of viewing evolution as information acquisition process. And for this, he's formulated a very nice way of thinking about the problem faced by evolution. And that's this idea of a population environment game. So as you can see, these slides were made last moment. In a population environment game, you can imagine a big payoff matrix with the rows indexed by the various strategies available to the evolving population. So something like the different types that are present in the population, and the columns indexed by the various microenvironmental settings that those types in the population might encounter as they're going about their evolution. And then we summarize that whole thing as a game matrix G. So it becomes a game between 2 players. One player is the population, which plays a mixed strategy corresponding to its polymorphic distribution of types. And there is some other mixed strategy XT played by the environment. And I like this model a lot because a lot of the more standard models we're familiar with in evolution can be expressed relatively straightforward in it. So for example, if we say that as time goes forward, the environmental distribution remains constant, i.e. it's the same as a time step before, we get the classic model of static fitness landscapes. On the other hand, we can imagine the environment can vary its strategy and it has full knowledge of the population. And if it sets its strategy to be equal to the distribution of the population for a square matrix, right? So we assume in this case that n equals m. If the environment sets its strategy to that of the population, we get effective evolutionary games, right? So I usually refer to this as a population involved in self-play, but it's also, you can see it as a population setting its own microenvironmental challenges based on the distribution of agents in that population. And finally, of course, you can recover Katerina's model by, if xt is under some arbitrary control, some adversarial control, then we get the tumor-doctor game. And we can imagine the population PT is evolving, and we as the doctor are choosing which column to challenge the population with, corresponding, say, to different treatments or various other things that we could do to intervene. Now, in this setting, we clearly want to know what's the relative power of the two players in this. One player playing, replicator dynamics to update its population state, and the other player being an arbitrary physician that can change whatever they want. Now, unfortunately for us, and fortunately for evolution, Ryan has showed that there's a sense in which the population player, i.e. the tumor in our case, is actually an optimal player, optimal maximizing a certain kind of fitness. So that's not really a good sign for us. It means that we shouldn't underestimate the tumor's ability to play this game. It's actually very, very, very good at this game. So how should we respond to the tumor's optimal play? Well, the standard approach, which I think everybody in oncology is familiar with, is just to make new drugs to continue changing that matrix G to the point that any strategy the tumor could take ends up being bad. And then it doesn't matter if the tumor is playing optimally or not. If you can just make all types unviable, then the tumor won't do very well, and that'll be good for the patient. Of course, we know that this is sort of an impossible goal. Whenever we come up with a therapy, almost always there's some type that's resistant to it, and that type emerges out of the treatment during a relapse. So the strategy that adaptive therapy has taken is to improve how we pick our distribution over the existing drugs. And here the hope is that by improving our strategy, we can force a setting where the best tumor strategy is bad for the tumor. This is also sort of a hopeful strategy, but to some extent it is promising, because all we have to do is outperform the maximum tolerable dose, which keeps X kind of fixed throughout the whole treatment. And we have these extra degree of freedoms to vary our treatment, so we can expect to maybe find potential. But because the tumor is playing optimally, it's not clear that this will always lead to a victory for the physician. And I think there's a third strategy which we neglect sometimes. And this, I don't know how skilled all of you were at sports when you were a kid, but if you're as skilled as me at soccer, you probably often heard, "Oh, don't worry, it's not about winning, it's about having fun." And I think this is something that we should take very seriously in our play against the tumor. In particular, we shouldn't give in to the tumor's definition of what success is. So the tumor is optimal at maximizing a certain kind of fitness, which is closely related to the tumor size. And a lot of the models we build try to control tumor size, try to minimize it or keep it at a certain level or put it long as possible before it escapes, etc. But it's not the tumor size directly that we care about in the case of the patient. We care about adverse effects of that tumor size on the patient. So the primary thing that we care about is bad things happening to the patient. And it doesn't always have to be the case that bad things are due exclusively to the size of the tumor. There could be strategies where we push the tumor into a phenotype where it is not hurtful or not as hurtful to the patient while still continuing to grow. So the idea is to, for example, try to make tumors benign again or some such. Unfortunately, this is not very compatible with how we currently design drugs, because usually if we want to approve a drug, the easiest way to do it is to show that there's a response in the tumor size to application of the drug. And so we're always kind of making drugs that are trying to beat the tumor at what it does best. And one of the strategies I think we should examine as people working on adaptive therapy is changing our goal in the game, and thus not having to play against the tumor on its own terms. So that to me is sort of tells a little bit about the relative power of the two players. We shouldn't underestimate the power of the tumor, and we shouldn't overestimate the power of the physician, but we should realize that the physician does have some tricks up our sleeves, in particular of changing what we consider to be success. Instead of beating the tumor at its own game, beat it at maximizing damage to the patient. Now, the other question, of course, is how do we know the rules of the game that's being played? And for this, I learned a lot from Chia-Hua. She's a philosopher of science, and she approached me about a year ago because she was interested in tool migration, and mathematical oncology seemed just like the place to look at tool migrations in action, right? We have tools coming in from game theory, from experimental microbiology, from all kinds of parts of cancer, from dynamic systems, etc. And one of the fascinating things about looking at tool migration is seeing how the narratives and methods are adjusted in response to the field's pressures. So for example, when we're doing evolutionary game theory outside of oncology, thinking about abstract cooperation among, let's say, various animals or humans or something, we're generally going for general models, and we don't worry as much about precision and accuracy. But when you're working, let's say, in a cancer hospital, you really start to care a lot about the accuracy and precision at the potential expense of generality. And we've probably all felt this if we've moved from a math department, let's say, to a more clinical setting where our terminology becomes much more precise. It's no longer consider signal X, now it's consider the molecule VEGF, right? And this change in narratives accompanying our models helps us to better connect to the experiments carried out by our colleagues. But it's not the only thing that we can do. And for this, it's useful to think about a nice definition of modeling. And for this, I want to quote extensively from Michael Weisberg, who writes, "Modeling is the indirect theoretical investigation of a real-world phenomena using a model. This happens in 3 stages. In the first stage, a theorist constructs a model. In the second, she analyzes, refines, and further articulates the properties and dynamics of the model. Finally, in the third stage, she assesses the relationship between the model and the world if such an assessment is appropriate. If the model is sufficiently similar to the world, then the analysis of the model is also, indirectly, an analysis of the properties of the real-world phenomena. Hence, modeling involves indirect representation and analysis of real-world phenomena via the mediation of models." And to me, this seems like a very clear and elegant way of saying what I feel like I'm doing when I'm doing mathematical modeling. It really captures these things. At first, I construct a model. This model is often inspired by my intuitions about a biological system or by prior work on that system. Then I focus on my model, I analyze it, I figure out its dynamics, I figure out the robustness of the model. And finally, I see, is there some fit between the results of my model and some results in experiments? And by adjusting our narrative to be more focused on the biological details, it makes this step much easier to do. But this isn't the only way that we can approach modeling. The big point of Weisberg's article here is that instead of doing indirect representations, we can also do direct representations. And so what would a direct representation look like for game dynamics happening in cancer, it would require us to combine building an experiment and the actual model, or not the model, but the representation of that experiment at the same time. So how do you do this? For example, by direct measurement with the game assay. So here I drew a little cartoon. If you don't like my little circles, imagine the vials that Elsa had in her talk, and imagine that one type of cell, let's say the resistant cell is in pink over here, and then the other type of cell is, let's say, I said that's resistant, so this is sensitive. Sensitive is in blue over here. And we imagine making several different vials of different proportions of them. So maybe this proportion is 100% resistant, 100%, and this proportion is 100% sensitive. This one is 50-50, and maybe this one is 66-33, and this one's 33-66 or something. And if you're doing a real experiment, you'd probably have a lot more than 5 proportions to start with. Maybe you'd have, let's say, 10, 15 proportions spread out across the range of the different mixtures you could have made of your 2 types that you want to measure the game between. Okay, well, that's our independent variable. So we throw that on the x-axis and we label that P for the proportion of blue. And on the y-axis, we're going to measure the fitness of each of the 2 types in each of these proportions. So throw some data points on there. Obviously, this is just a cartoon sketch. Then do a line of best fit. In this case, it looks like a line fits well. So do a line of best fit. Those 2 lines are then our fitness functions. And from those fitness functions, we can start to recreate the game. So in blue here, we have the fitness function for the cell type C. I was calling them sensitive, but let's call them C now. And in the pink, we have the purple, we have the type D cells. And from that, we can get the game that's happening between these 2 just by looking at these various parameters of where the endpoints of the line cross 0 and where they cross 1 proportion. And that together gives us the payoff matrix for the effective evolutionary game corresponding to this system. Alternatively, if we just want to plot the point in game space, we can look at the gain function instead. So the gain function in this case is just the fitness of C minus the fitness of D, represented here in gold. And from that gain function, we can get a game point in a 2-dimensional game space. And we'll see this come up later when I give some experimental examples. So what happens if we do this, let's say in non-small cell lung cancer? Well, we did over 4 different conditions. We have, no drug over here, drug plus cancer-associated fibroblast over here, alectinib over here, and alectinib cancer-associated fibroblast over here. And in all those conditions, we end up getting some sort of fitness function for each case. And those fitness functions can then be plotted into a game space. And we can see these are we're not modeling the game that's happening. We're literally just taking something that started as 60 gigabytes of images from which we got the fitnesses, from which we got the fitness functions, from which we got these points. So it's really just a very fancy summary statistic of our raw data. But already from this, we can start to see different types of dynamics. We can see different types of games in this, where games in the upper quadrant up here have a different dynamic from the games in the lower quadrant here. So in our case, the DMSO plus CAF condition is qualitatively different from the other 3 conditions. And I won't dwell on this too much, but it really lets us directly measure the dynamics and say, look, they're different, their error bars don't overlap, etc. Oops, this is the second slide. And so how does this fit into Ryan's view of the population environment game? Well, we can take our big purple game matrix and stick the game corresponding to each possible drug combination we could have given. And that becomes our whole big matrix where the row is selected by the distribution of sensitive cells in the population, and the column is selected by our doctor. But there's restrictions on how the doctor can select. The doctor actually only has 4 options corresponding to the 4 drugs. And those don't correspond to picking a single column, but picking a subspace on each one, a 2-dimensional subspace, and they're playing the population strategy. So this lets us know that the doctor's movements are limited in this game. You can imagine further limits. For example, to get rid of CAFs, you might have to administer a therapy which is not reversible. You can't reintroduce CAFs, let's say, back into your system, in which case you could only play the blue strategies before playing the red strategies, just because once you've eliminated CAFs, you can't go back and reintroduce them, for example. So you can imagine there's a lot of these restrictions that are on the placed on the doctor, not to mention the doctor not always being able to know this distribution that they're playing against. But this is kind of how you could view this as adaptive therapy against the population. And in this case, it's not very promising for the patient. Kind of no matter what you do, resistance emerges. So about a year ago, last summer, Ranjini was visiting Moffitt, and she got excited about the game assay. But unlike me, she's much more of a biologist, and she cares much more about the actual biological processes that go on to shape those payoff matrices that we're getting. And in particular, if you look at how alectinib acts, one of the ways to get around the pathway alectinib blocks is by introducing HGF. And we had a reason to believe that HGF matters a lot because the cancer fibroblasts were producing HGF, and that's why they were offering a protective effect, which I didn't go into detail on the previous slide. And so Ranjini really wanted to focus in more on this. And so she asked, how else can we modify this game matrix? We can add more treatments, etc. That's increasing the M here. But we can also engineer new strategies for the population. We can just extend the matrix downward. So she took the 2 types we already had, the sensitive and the resistant, and engineered a new type of producer cells, which were another non-small cell lung cancer cell, but engineered to overproduce HGF. And now you have this 3-strategy game in the population against the various treatments that we might offer. And that's interesting to look at because it pushes us out of this easy 2-strategy setting into a richer setting. And we can start to look at the games pairwise. And if you look at them, they're not particularly exciting in any given setting, although in the sensitive versus producer setting at the bottom, it makes less sense to model them as a linear game, and you want to try doing a nonlinear game, maybe a piecewise nonlinear game was the one that Ranjini was interested in. And then the question becomes, from these measurements of 2 strategies, can we recover the 3 strategies? So can we get this kind of matrix that's this kind of game dynamic on the 3 strategies? And this kind of game dynamic is interesting to look at because it's qualitatively different from what we were seeing with the 2 strategies. With the 2 strategies, we were always seeing sort of a single basin of attraction. The populations either went to all resistant or went to a mixture of resistant and sensitive. But with three strategies, you get these 2 basins of attraction, one of them labeled in blue and one of them labeled in red, with the blue one going to a mix of sensitive and producers and the red one going to a mix of resistant and producers. So in this setting, you start to get a game matrix where you can start to, when you give this treatment, potentially move the population away from resistant phenotype to a sensitive one to try to resensitize the population. Now, against this, we might ask, what kind of strategies, tactics does the tumor have available to it? And one of the ones that we often discuss is this idea of competitive release, which Nathan was really excited about and taught me a lot about. And so the vague idea of competitive release is that decreasing the sensitive subpopulation in some way helps the resistant population, or conversely, increasing the sensitive subpopulation hurts the resistant population. That's sort of the vague idea. But now that we're directly measuring and representing these games, what will this look like sort of formally? Well, there's sort of two ways that we can go. We can do an absolute fitness definition or a relative fitness definition of competitive release. If we look at the absolute fitness definition on the left here of competitive release, it means that the fitness function of the resistant type has a downward slope. So as the proportion of sensitive increases, the fitness of the resistant decreases. Alternatively, we can ask for a relative fitness definition of competitive release. And here it'd be the gain function that has a downward slope, so the difference between the resistant and the sensitive. Notice that these two definitions are not equivalent. So for example, on the right, we could have had a resistant population with an upward slope, but a sensitive population with a bigger upward slope. And that would give us a downward slope in the relative fitness, right? And similarly in the absolute fitness, we could have had all kinds of weird slopes for the relative fitness. For example, if WS went up like this, then the wrong correction. If WS went down faster than WR, then you'd get a gain function that's sort of going upwards. That's the gain function. So these two are sort of two different definitions, and both of them are compatible with, if we go back to the sort of 60s mollusk's view of competitive release, both of these definitions are compatible with it, mostly because a lot of the early work in competitive release is focused at populations at carrying capacity, where there's not much of a difference between absolute and relative fitness. But if you're looking at populations that are in the growth phase, there's a very big difference between absolute fitness and relative fitness. So what did Nathan do with this? Well, he did a heroic effort where he measured a whole bunch of games in a whole bunch of different drugs, and couldn't find any absolute fitness competitive release, but could find a number of cases of relative fitness competitive release. And the nice thing about this relative fitness competitive release is that it depends only on the gain function. And we saw before that the gain function can be read off of the game matrix space. You can just plot all the games in the game matrix space, and anything that's below this purple line, to the left and below this purple line, would be a case where competitive release happens, and everything above it is a case where it doesn't happen. And we can see that, for 3 of the 12 conditions that are listed in this particular case, Nathan saw competitive release. So definitely we can examine very methodically some of the tactics that we attribute to the tumor, and see under what drugs are they realized and what drugs are they not realized. So in conclusion, what have we learned from Ryan, Chia-Hua, Ranjini, and Nathan? Well, we learned about the relative power of the two players. In particular, Ryan told us to not underestimate the power of the tumor. It's an optimal player in some very real sense of the word. And if we want to do well in play against the tumor population, we have to be very creative. And one of the ways that we could approach this is, for example, by redefining what we see as winning for us. And then what about the rules of the game that we're playing? Well, Chia-Hua, Ranjini, and Nathan showed us that we can measure these rules directly, and we need to measure these rules. Otherwise, we can't win a game where we don't know the rules. Thank you.
Okay, thank you very much for, I would say, inspiring talk. And I will try to not ask these first questions myself, because I would question a lot of things you said, I guess, which you would expect. But I will start with the questions from the audience. Mm-hmm. So first question is from Sandy Anderson, and he's saying, does the environment tumor game assume the tumor doesn't modify the environment? And if that's the case, do you think that modification could be included?
No, it doesn't. It does not assume that the tumor does not modify the environment. Let me restate that without the double negatives. The tumor environment game can account for the tumor modifying the environment. In particular, the setting where we were talking about the how to implement effective games using this model is a prime example of where your microenvironment is set by the population itself. So definitely those cases are accounted for in the tumor environment game.
Okay, then we have next question from Heiko. Heiko, yep. So what happens when the game functions are not linear? Do you lose valuable information by just looking at the linear values, or is the delta of these functions, so the slope, all that matters?
Yeah, you can lose valuable information in the nonlinear case. In particular, the representation of two-dimensional game space becomes sort of moot, because now you have your function needs more than 2 dimensions to summarize it. The only cases where this really matters is if the nonlinear gain function you have goes up and down over the 0 line of relative fitness. Then you can have these internal fixed points that you wouldn't have expected from just the from just the linear game. In our case, a lot of times the linear game is a good description. Sometimes it's not, but it depends on your system as to what order of game you want to look at.
Okay, and then I move to Jeffrey West's question. So how might you extend the frequency-dependent evolutionary game theory assay to include density-dependent effects? I would actually also ask this question if Jeffrey did not. So
yeah, it's straightforward to extend the density-dependent effects. All you do is now you have 2 independent variables, proportion and seeding density. Of course, that's easy to say as a theorist because I don't have to run all the experiments. But if we're imagining for good resolution, we were running like 8 to 10 different proportions on our x-axis. Now you're imagining a second dimension where you should probably run, 8 to 10 different densities. You cross those as 100 different conditions in which to run your experiment. Suddenly your experiment becomes much more expensive and much more time demanding, but not in any way infeasible. I hope that answers the question.
Okay, yeah. We will see whether a new additional question pops up. But Yannick Viozat is asking another question. So in order to minimize the resistant population, isn't the absolute fitness more important to consider than the relative one?
Yeah, I agree with you, Yannick. I think the absolute fitness is more interesting, especially in the case of an in vivo population. All of the experiments I described are all in vitro experiments, and in vitro experiments, sort of the way we set them up so that pretty much everybody, we make very like generous conditions for the cancer cells so that they do, we try to keep them maintaining positive fitness, because that makes sort of the computer vision and all those other parts of just processing the data easier. So I agree that in the patient, we should look at absolute fitness. In the Petri dish, it's more moot, it's relative fitness or absolute fitness that matters. But the important thing is that at carrying capacity, the two concepts become the same, because if you're remaining in carrying capacity, every gain you gain in absolute fitness has to be offset by the same loss of somebody else in absolute fitness, and thus it's the same thing as relative fitness. And so the hope is that some of these measurements of relative fitness translate to settings where we're at carrying capacity, but we haven't played with that yet.
Okay, thank you. Liu is saying, impressive talk. And she has a question on your resistant invader. Okay, what does invading mean here? If you co-culture cells in the assay, what you see is a cell migrating. So what is actually the invasion there?
Yeah, so this is from the labels, very good eyesight. I think it's from the labels of this figure, where we say relative fitness of resistant invader and relative fitness of parental invader. And the idea is that what we're plotting here are these points that are the reason we need to do an assay. We can't just get those without measuring a fitness function, is because they come out of, if we go back, these quantities, these yellow, these bars here. And if you see, these bars only have one data point and an inferred intersection. And same here, data point and an inferred intersection. And so when I say sensitive invasion, what I mean is, suppose we're in this setting, if there was just one cell of C-type or sensitive type, how much higher would its fitness be? And in this case, it'd be a lot higher than the resident population, and similar for the other one. And so that's why I call those the invasion fitnesses. You can also say it's relative fitnesses in the limit as the proportions go to 0, or relative fitnesses in the limit as the proportion goes to 1.
Okay, we are slightly already over the time, but I cannot help it. I will ask you just one question. So when you mentioned this invasion fitness, there is the whole theory called adaptive dynamics, which actually studies, invasive fitness. So invasive population, which would be your cancer here, versus resistant population. And say the father of adaptive dynamics, who is Hans Metz, asked this question in a famous paper: when does evolution optimize? And his answer is never. It's never an optimal player. Have you had a chance to read it, or?
Yeah. So for this, I want to defer this to Ryan, because I think I don't want to. This work isn't quite ready to go yet, so I don't want to spoil too much of it. But when I say optimal, it's relative to a specific definition of fitness, which is not the same one as the one used by the adaptive dynamics folks. And it's also a certain kind of hindsight optimality, which is also not how adaptive dynamics handles their statements when they're saying, is it optimizing? So is something optimizing or not depends on what you're asking is being optimized and what you count relative to what you count optimal being. So in this case, it's a slightly different kind of fitness that's being optimized from adaptive dynamics. And the criteria for being optimal is also much more hindsight focused, with the environment kept, the variable
so
environment.
Is it more general or is it more specific?
It's different.
Okay.
But it does map onto, in most models of adaptive therapy that I'm familiar with, the whole point of this was to say that the thing that we're tracking in those models is actually the thing that the tumor is actually very good at optimizing. And so it's actually a hard thing to fight against. And in most models, it does line up with the population environment game definition of optimization.
Okay, thank you for answering all the questions and also for the great talk. That also means that we arrived to the end of this session. So I would like to thank all the speakers, but also all the participants. And I'm